SAREF4ENER, continuing from last time presentation where we looked into the SAREF core, the main module, horizontal module. So today we are going to see one specific domain of interest of SAREF. So we will tell you a little bit about what it is, SAREF4ENER, what's the history, and what are the standards on which SAREF4ENER is based on. Presenting also the use cases. What are the main concepts of this model of SAREF4ENER? There will be some diagrams similar and visualization similarly to what we did last time for SAREF. So you will see some diagrams with the classes, and we will present you also some example of devices, because somehow with SAREF4ENER gets a little bit more complicated, the story, because it's a domain model. So SAREF was more general and on purpose kept a little bit easier and simple, like building blocks, but now we are going to more specifics. So there is a little bit more that we need to say also about SAREF4ENER and its concepts. And then there will be references and further reading, because then you can find the proper documentation if you are interested in. So SAREF4ENER, it's SAREF, so it's the Smart Application Reference Ontology, extensions for the energy domain, and even more with focus on energy flexibility. So it's energy, but also we could say energy flexibility. What we do with SAREF4ENER is to optimize with flexibility in general, consumption and production, based on what are the device specifications, but also what are the signals coming from the grid, and also customer configurations, because the comfort and the instructions basically of the user should always be taken into account when offering flexibility. It's also an open standard, as it is SAREF. Which is maintained by the European Telecommunication Standardization Institute, ETSI, and there is a website where everything is documented, and you can find it there. SAREF4ENER, why? So what are the main benefits? As any other SAREF module, it's interoperability, but in this case, it enhances the communication between a specific type of devices and systems. Therefore, those are the energy management systems and smart devices. And facilitates the integration of various protocols and standards, because there are several standards that can be used, that exist. But in this case, SAREF4ENER is a semantic layer on top of that, so it can be reused with different standards. Benefit is obviously energy flexibility, because that's the domain we are tackling, we are trying to capture with SAREF4ENER. So meaning that by having a common understanding on this data exchange on energy flexibility, then there should be higher efficiency, because the energy usage is better balanced, maximizing the usage of renewable sources, local energy produced locally, and reducing the overload that usually is on the grid, which is of course a problem. So as a third benefit, there is the one of sustainability, because of course this is enabling more sustainable solutions in general for the society, but also because here we're talking about system and machines exchanging information, but already having this type of models, it's helping to create awareness of energy usage with the consumers. Consumers that have so many different devices and systems at home, and usually most of them don't even know how they work, or they have 4 apps in their phone, they don't know how they interoperate and so forth. So they even promote sustainable energy practices, because by doing things we see that people start to learn, okay, I shouldn't charge then my car just in the evening at 5 o'clock, 6 o'clock when I go home, because everybody's charging my car at that time, or I used to do the laundry or dishwasher in the night. Now maybe I have solar panels, and then I just do it when the sun is just shining and all things of this type. Standardization is obviously another benefit because it is standardized, governed, evolved, and so forth, as we mentioned, by HEDGE. But it is also used as in policies, so in regulations. And in the specific case of SAREF4ENER, it is being used, adopted as basis for the European Code of Conduct for Energy Smart Appliances Manufacturers. If we have some time later, I will be happy also to tell you something about that. But there are some references at the end of the page of the presentation anyways. So SAREF4ENER is based, it's a development that started 10 years ago together with the SAREF, because it was the first use case that we started to explore together with manufacturers and industry associations already at that time. The result is that there were already standards being used in this area for energy flexibility, demand response, and so forth. And two of them, you see them named here. So the EN 50631 and the EN 50491 12-12. One, it's difficult to remember the numbers, so let's call them SPINE, the first one, and S2 is the second one. I'll tell you in a moment where these names are coming from. But the SAREF4ENER was developed over time, because it's a long development starting years ago. At the beginning with the Industry Association of E-Bus and Energy-Atom, which are industry and manufacturer associations. E-Bus was mainly originally based in Germany and Energy-Atom in Italy. And they asked us to started creating SAREF4ENER to find harmonization of their different data models. And later on in the years, we started integrating also the S2 standard with the S2 consortium, where some companies like associations like KNX and also the Flexible Alliance, Power Alliance are part of the S2 consortium. And we developed also in the context of the HEDGE-2020 Interconnect project, which was a project mentioned several times in the context of HEDGE-IoT, because some of our partners, including TNO, come from that and already experimented with the interoperability solutions there. SPINE, here you have some more information about SPINE. And you see also which committee, technical committee 59X in Sensenelec has developed it, which with the name and so forth. What you need to know is in general that it defines the exchange between smart appliances. So we are in the home premises with the communication between smart appliances, management systems in homes and buildings that include also the energy management. Since part of this standard of the N55631 is called based on something that is called the SPINE language and protocol. In short, this standard is also known as SPINE, and we will refer to it as SPINE. Main promoter of the SPINE specification and of this standard, although developed in Sensenelec, is the E-Bus Association, and you can have a look at that also, what are the partners. The other standard is what we have called S2. Why S2? Because S2, there is the European smart grid architecture that there are various interfaces in that, and one is the S2, and S2 is the interface between the energy management system and the other equipment in the building. So there is a picture in a moment that I'll show you, so it's really clear where this S2 standard is positioned. Important thing is that it's another standard, so we already have two different standards that need to be with they have similar concepts, but not always. Sometimes there is an overlap, sometimes not. But semantically, they have an overlapping conceptually. And that's what we have expressed by adding SAREF4ENER on top to harmonize those. And we believe, actually, we're already pretty sure because we have experimented with that even other standards or companies, organizations that are not using that can rely on these concepts that we have expressed in SAREF4ENER and in an efficient way, because conceptually we are able to express with that. Some more information about S2 can be found on their website. But I think this is a nice picture to show that it's also used by, actually made by the S2 people in their website, which shows how we are at the home premises. So what we mentioned is that we have energy manager, customer energy manager. We have the different devices, PVs, we have heat pumps, we have EV chargers, smart meters, home batteries, you name that, HVAC, heat pumps, and so forth. But this is, anyways, there is a connection also with the energy system and everything that is in there. So distributor, system operator, TSO, and aggregators, and anything else, and even the market and so forth. So it's important because the flexibility is something that it's shared in combination here. SAREF4ENER, there are several versions, but just to give you a little bit of history, is the first version was developed in around 2015, 2016, and was based on the concept of power profile. So each device has a power profile, so it offers makes available some flexibility, saying I need to do this, but this is the profile that I need to use, but there are some alternatives. So it says to the energy management system, says choose the one you want as long as certain conditions are met. With time, we in the various versions from the 1.2.1 onwards, which we developed in Interconnect, we added and harmonized also concepts from the S2 standard, meaning that then, together with the power profile, that it's also used by S2 and harmonized in SAREF4ENER, but then we added things like power limit and envelope. We will go through these concepts in the rest of the presentation, and Cornelis will guide you a little bit into that. But the purpose here is to show you on a high level what's contained in the standard. Plus some other type of profiles, because depending on devices, if we have batteries, if we have buffers, if we have storage indeed, or other type of devices, there are different way of operating from these devices, and we can capture them with different profiles, because not all these devices, EV charging and so forth, not all these can use power profiles. So there are other ways that are captured then in the current version of SAREF4ENER. There is also some part where there is a negotiation of incentives by an incentive table that it's mostly part of SPAN, because actually S2 doesn't cover that part, but we decided to include it anyways in SAREF4ENER. And there is the lower part is about the flexibility communication between parties and components. So starting from the fact that there is one of the components, which could be the energy manager or could be the DSO, is asking what is your flexibility. So asking a device or something else for what's the possibility in the availability in flexibility. From there, a flexible offer is formulated, because then there is some intelligence algorithm that it's deciding, optimizing the energy consumption, production of various devices and systems, and deciding that that's the offer that will be chosen. And as a consequence, a flexibility instruction will be sent for the actuation of that specific offer. And that's a little bit what SAREF4ENER covers. use cases, we always start from use cases. So also in the case of SAREF4ENER, that was the case. It doesn't mean that these are the only use cases, but can cover more. But those were the one used as a starting point. Question to you is, what use cases do you recognize for your pilot? Because starting to think what use can you do of SAREF4ENER, if any, and also started to think about more interoperability use cases, transversal in the context of the discussions that we are having in the project about transversal use cases, where services and use cases can be reused throughout several pilots. Those are the use cases on which SAREF4ENER is based. So like flexible start of smart appliances, so users that set some constraints in the usage of that. So saying, I put my laundry in the washing machine, do it as long as it's ready by tomorrow 9 o'clock, or I want hot water because I take shower in the morning, the rest of the day do whatever you want, or I charge my car, do it whatever you want, but I need to have at least 80% of the battery by 5 o'clock in the morning, things like that. So a delayed start, a flexible start of smart appliances and devices. Then there is the part of monitoring and controlling smart appliances and not reaction to smart grid requests in case there are also incentives for adjusting power consumption and production consumption based on things that are happening, signals from the grid. Limitation of power consumption, because sometimes there are power limits, use cases with power limits to be set by energy manager, manufacturers, or and of course the contractual agreements that can be made. Incentives, so that's another case of incentives when we use the incentive table that I mentioned before. And in general, energy flexibility, where energy flexibility is, well, usually it's the capability in which the customers offer the flexibility to the grid of changing also the consumption depending on the grid signals and the time of the day and the market price and so forth. In this case, this energy flexibility can be captured between devices and the energy management system, EMS. But also we have done this also in the context of interconnect directly with the DSO. So then the DSO can manage the electricity. So these patterns of offers and instructions and requests that are being sent. So the DSO can also is the DSO side of the flexibility. That's what I'm trying to say. That there is the premises part, home premises, but then there is also the DSO that can manage the flexibility. Then this is a picture that maybe you've seen already, but just to remind that SAREF is a framework. So what we're seeing now, last time we've seen the horizontal part, which is SAREF core with more foundational common concepts. And what we're seeing here now, it's one of the extensions, which is SAREF4ENER. And we are explaining what this is, a specific extension. So meaning that the SAREF core and SAREF4ENER or whatever other extensions we are using, it's a core, these inner circles that are standardized and maintained and evolved by HEDGE. But in HEDGE-IoT, we are building things that reuse, overlap, or can extend also something that it's in SAREF, but also based on other standards, because we have mentioned other standards in HEDGE-IoT that are used, also probably more on the DSO side, because a lot of pilots are on that part, which doesn't necessarily need to become a SAREF standard, but it's interesting to see in our models which standard and how we start combining even concepts from one model and another, if it's with the IC SIM or some other IC standards that are used. And extensions then can be done, and then those can be kept just as our model, your model, HEDGE-IoT model, or we can think later, even if we bring it back to standardization and have something become part officially of the SAREF suite framework or ontologies or not. Now, I think we start looking a little bit more at these models, but maybe it's a moment to ask if there are any questions, because I've been talking for a while now. Okay. Okay, then now we start going into the details of the model. So for completeness, I have to say that this part that I'm going to present now is not actually present in S2 nor in Spine, not because it's more about the message exchange, the part of the flexibility offer, request, and so forth. And both standards use this, so they both agreed from both standards that this is good. But this is also something that by experience we model based on the experience also in the interconnect project, indeed also with the DSO and with the other parties in exchanging flexibility. So that's why we called it flexibility communication, because it's the first part in which flexibility is negotiated between components. So the story starts that there is a flexibility request created at a certain time, produced by some agent and with some recipient. This includes something in it. It could be an incentive table, a flexibility profile, time series as data point. The message here is that it includes something that it's also contained further in SAREF4ENER, and we are going to see it in a moment. What are these things? So it's a wrapper for a request that comes from somebody saying, so what is your flexibility request? And this is also an effective period because it is a flexibility in a period of time. Then there is the part, of the flexibility offer. Now, this offer relates to a specific request that has been already sent. So you see a relation that goes that a flex offers relates to a certain request, an instance, a specific instance like the request 1, 2, 3 that arrived yesterday at 3 o'clock. This flex offer is also produced. So there is the provenance data, basically who is produced, who is the recipient, and so forth. And it has also an effective period because then the request was done at a certain time, and this also, and as the flex offer, it's an offer for this certain effective period. And the content, the payload of the flex offer is again one of these components, incentive tables, flexibility profile, and series of data points that we will explain in a moment. Then there is the third part, which is okay. So if this was the offer, then this is the instruction that this should be activated. So as you can see, the flexibility instruction refers to the offer. So what we're saying here is that each activation plan, its instruction refers to a certain offer that was part of a previous request. So you can track and relate all the instances together. It contains, well, it includes also, this is in this case, it's really with an execution time because it's an instruction to be executed. So this is the plan, the offer, the profile that is going to be actually executed on the device at a specific time. And there is a status because it could be accepted or I don't know, even read it. It's a bit small, but okay, there are all the possible states in which this instruction it is. But that's the execution of the instruction on a certain device or system. And this is, again, it tells you see time series and ENSA cost, because then together with this there is an activation plan which is attached as value in time series, and a cost, because at the end that's what we do. There is the flexibility in time of what is the amount of whatever energy power, but also what is the cost of it attached to that. I think for now I finish here, and now it's time of Cornelis to go, because now we start to go into all the concepts that we have seen until now. So I'll close here.
Yes, thanks a lot for Laura for the very useful introduction to all the history of SAREF4ENER, the reasons why we made it, and the standards that it's based on. So now we'll get into a little more of the main concepts and a little more into the main flexibility profiles that are provided in SAREF4ENER. And so these are also the ones that you can reuse in the pilots that you're working with. And so that's also something for you to constantly keep in mind with every part of the model that we explain. Like, is it something that is usable or applicable for a part of your pilot? And so the next two, beyond the flexibility communication that Laura just explained, is first of all time series, and secondly, the various flexibility profiles. Because time series, we found that that was needed as an extension above the SAREF core, because SAREF core was mainly considering single measurements or single observations. And I think you can now see also my pointer.
Yes.
Great. The SAREF observation, which is specified here, and then here the data point and the time series are provided as a specification of that, such that because we found it in the concept of energy, it was especially important to also be able to model time series, especially when talking about forecasting. Because forecasting, of course, is a major part of energy flexibility, because we want to have a forecast of both energy production by, for example, solar panels, as well as a forecast of energy consumption by all the other devices that you may have in your network. And that's why SAREF4ENER has provided a concept for a time series, as well as, it may be a little small to read, but as well as concept for an update rate, for concepts on how long a particular forecast is valid, as well as usage, so additional information on whether this forecast is an average or a maximum or a minimum information, or maybe whether it's a set point that you want to configure. And also information about the device or user that reflects the provenance of such a forecasted time series. And secondly, we have the flexibility profiles. And the color coding you can see here in the flexibility profiles reflects a bit of the history of SAREF, because in green you can see the core concept, so the core concept of a profile that has been defined in SAREF core as a profile to which a device can adhere. And then in blue, you can see the concepts that were already in the very first version of SAREF4ENER. So, for example, a device that's, of course, both in SAREF4ENER and in SAREF core, which can exhibit a particular profile. And among the flexibility profiles, you can see here that it is only the power profile that was in the first version of SAREF4ENER, and that in the updated version that was published in the European Interconnect project, we extended it greatly with various other flexibility profiles, of which I will explain in which situation you may use either of those. But you can recognize those names from the overview of how SAREF draws from both S2 as well as from EEBUS. This picture is the one that I meant. And because here you can see exactly that initially it was only the power profile, and then we extended it with incentive table, with power limit switch envelope, with fill rate, with demand driven and operation mode. So I will go into these in detail, but the question for you is which of these types of flexibility could be applicable for your network, for your devices, or for the systems you provide. I heard some noise. Was there a question, or was it just an accident? Otherwise, I'll just continue. And let's first go into the power profile. And the power profile is a way of describing which programs a device may have that it runs consecutively, and also a set of programs and power sequences from which a device may choose during its operation. This one may particularly be applicable on white goods. That's why I've shown here a collection of them, because this would be particularly applicable on washing machines, dishwashers, that would have particular very intense programs, as well as several eco-friendly programs. And then the type of flexibility that it could provide could, of course, already be the example of the early start that Laura mentioned, but it could also be concepts of an intermediate pause between programs. And with this power profile, you can model all those options, such that after that an energy management system can choose among all those alternatives. That's also a reason why you see here various alternatives groups mentioned in the model, of which one is most applicable for the current situation of the energy consumption and production. And within those groups, you can have various power sequences, and all of those can have a status, like you're completed or something is paused and has to be restarted. And then the most detailed information of such a slot within the power sequence about exactly the energy that's being used could then be modeled in a SAREF property value. Particularly the SAREF property value, you can see that it's mentioned here in green in the box. So that means that it's really a concept from SAREF core. So if you may be a little unfamiliar with that, you can look it up in the presentation of 2 weeks ago. But like mentioned, this is a flexibility profile that's specifically for white goods. But we can also look at another type of flexibility, because other types of devices can inherently provide another type of energy flexibility. And so another one that is that we've modeled, it originally comes from S2, but we've also generalized from that a bit, is a fill rate based profile. And the fill rate based profile is specifically for all kinds of things that contain batteries, because a battery, of course, has a fill rate. And so that's why in this picture we have shown an electrical vehicle. Because an electrical vehicle is typically something that is being charged, and for which you can specify, for example, the speed of charging, a minimum or maximum level of charge that you would want. And specifically also in the Dutch pilot, we will be experimenting with vehicle to grid. So can the vehicle actually be used to supply power to a particular home or building? Because then it will effectively function as a battery for the electricity campus we're working here with. So I do not want to go into the details of this model, because it may or not be relevant for everyone, but I think it's important to highlight that there is the main concept here of the storage. And to the storage, there are a lot of concepts related, such as how fast it can charge, what the minimum charge level is, as well as indeed the leakage behavior element. How fast or how slow is it that the energy runs out if you don't actually use it? And you may also look here for example triples that we have provided along with the SAREF document. So that's on the GitLab where all the SAREF sources are stored for your reference. Another one which is slightly different and maybe relevant in quite some pilots is a demand-driven profile. So a demand-driven profile is a little different because you have to adapt to the demand that is being delivered to a particular device. So what does that mean? What you see here is the inverter of solar panels. And of course, the number of energy that the inverter can actually produce is very dependent on the actual weather. So demand-driven profile is not very flexible, but you have to adapt to what is given to you. That's also a reason why the model you see here on the slide is actually quite a bit simpler than a fill rate based profile. You can see here that, again, I talked about a forecast that such a demand-driven profile has an average demand rate forecast of what is expected to be produced, and that demand can be actuated by a particular actuator, which in this case would be the inverter that actually starts up whether the energy that is provided to it by the solar panels should actually be translated to energy and be made available via the energy management system. And again here, if you can have, of course, quite some solar panels in some pilots, and then we also have here example triples that show how a demand-driven profile would look like in SAREF4ENER. And yet another different one could be operation mode profile. And the type of devices that this could be applicable to is here you see a diesel generator. And diesel generators are often used to balance out the grid, because if there is a particular like a little too little energy, you can immediately switch it on to balance out other things. So then operation modes really means that there are a handful of modes like slowly or medium intensity or high intensity of generating energy. So that's also what you can see here in model. If we show some of the main concepts of the operation mode, and then also various transitions from slowly operating to average level of operating to a high level operating, between which an energy management system or a human operator can almost instantly switch. And again, here are example triples on the SAREF GitLab page. Then there's another interesting concept of the power limit and the power envelope. And it was particularly interesting because that was something that featured both in the SPINE standard as well as in the S2 standard. Although they had slightly different names. The power limit is particularly coming from the SPINE terminology, and the power envelope is coming from the S2 terminology. But we found such commonalities between those two that we thought that in the effort of interoperability and standardization, it was important to merge those into by reusing similar concepts. Because the concept that is common to a power envelope and a power limit is the concept of an allowed limit range, which you can see here at the core of this conceptual diagram. Because the envelope as well as the limits specify the upper limit as well as a lower limit of consumption, of either consumption or production that a device can do. And this is something which is not particular to a specific type of device, but rather it's sort of a simple way of implementing the flexibility of, for example, an inverter or an electrical vehicle. That's why I put those here on the slides, even though you've already seen those pictures previously. This power envelope may be a way of implementing the flexibility of an EV if the full flexibility of the fill rate-based profile may not be available for whichever reason. But so one of the differences between the power envelope and the power limit is that the power limit also considers situations like a fail-safe power limit. 1 second and I'll answer the question. Of a fail-safe power limit, because a fail-safe power limit that would be useful in a situation where a particular device would lose connection to the network. So yeah, thanks for answering. Indeed, you should be able to see the right slide, but I think everyone can also for themselves move to a separate slide, but somewhere you should be able to see at which slide I am. So I think everything is cleared up. But anyway, the fail-safe power limit is for situations in which the connection between a device and the network is lost. So you turn into a fail-safe situation where you only use a safe amount of energy. And then finally, there's one additional one that I want to cover, which is sometimes perceived as complicated, but it's an incentive table-based profile, because a table of incentives is a mechanism that Spine has introduced. And how it works is that you can specify above a certain level of energy how much costs you have for that. So the first bit of energy is cheap, because that is always being provided by the solar panels. Then a part of the energy is a little more expensive, because it's the standard amount of energy that's being produced by the grid. And the next level of energy that you can use is even more expensive. So that's a way of calculating at which point you need to switch to a different level of energy that's being provided. And there's more information about all of these found in the SAREF4ENER documents. And those are also freely available. Everything, all these diagrams, as well as the information that they gave about all these various profiles, as well as the information that Laura gave about the use cases that SAREF4ENER has been made for, can be found in the HEDGE technical specification. And here at the bottom, you can see a direct link to the latest version of this specification. And so the latest version is version 2.1.1. And there's a small disclaimer here on the side of saref.etsy.org/SAREF4ENER. You can see all the HTML documentation, but just there's also a link to a technical specification, but we're working on that, but the link is still to the old version, so don't get confused. And here in the slide, there's a link to the latest version. And additionally, as we have explained last time, for your reference, I gave again the link to the latest version of SAREF Core, where all the main concepts that throughout the diagrams you've seen in green, where those are all explained. And then we only wanted to highlight one application that actually I think we can be proud of from the SAREF team, which is really here a collaboration with both the EU in terms of governance and with the industry. And that's the EU Code of Conduct for Energy Smart Appliances, which was a voluntary initiative aimed at ensuring interoperability of energy smart appliances. So really a set of device manufacturers that are pictured here at the bottom of the screen. They voluntarily committed to exposing the data of at least one of their devices, really in terms of SAREF4ENER. And also at the bottom, you can see the link to the document where they have made that commitment. And also in the attachments of the document, you can see the examples of how their data would, in various use cases, actually map to the concepts that we've provided in SAREF4ENER. And also this code of conduct is particularly a way where both the people from the standard of S2 and the people of the standards of SPINE have worked together, because both of these concepts are also explicitly included in the JRC code of conduct.